Right, so in this video, we're going to talk about circulation, also known as flow. So from the previous video, we talked about different kinds of vector fields, and one of the more common ones we mentioned was a general spin field, which is given by this vector formula, negative y(x). And if you recall, to generate that field, one thing you can always do is pick points. So like usually around the origin. So if I pick 1, 0, my vector I'm going to get is negative y(x), so that's going to be 0, 1. I'm going to get a vector that's 1 unit long pointing up this way. If I pick the point 1, 1, I'm going to get the vector negative 1, 1. So that's negative 1 to the left, up 1. It's going to be going left and up, and so forth. And if you keep doing this, you end up getting this vector field you saw in the previous video, which the name sort of speaks for itself. It looks like it's kind of spinning around the origin. So now imagine we have, a lot of times we use, just for lack of a better term, a particle on a circle, x squared plus y squared equals 1, that's subjected to this force. There's all kinds of forces. You can talk about gravitational force. You can talk about magnetic force. We can talk about velocity, think of it as the flow of water in a river or in a lake, right? How would the particle move or circulate / flow, those words get used interchangeably, around the circle? So we can kind of envision that. Here's my circle, x squared plus y squared equals 1. And if I put on the same vectors that we just generated, you can see, hopefully, that if there was a small particle, let's say our particle was right here. This is our small particle right here. And I subjected this to the field, that the field is kind of pushing it. And let's say it has to stay on this path, right? It has to be on the circle. It's getting pushed. It's going to get pushed, and it's going to travel around this circle, always around forever. So how do we quantify how much circulation or force is causing that particle to move around the circle? If we take sort of a microscopic look at, let's say, this moment in time when the particle's here, here's my curve, that's my r of t, my circle. As it moves, it's going to be moving tangent to the circle, right? As it moves, because it's stuck on the circle. So its initial movement, I know it can't go off the circle, but its initial movement will be tangent. So that's what t means. That's a unit tangent vector to my surface. Now, unfortunately, this example isn't great for showing this, because in fact, my force field is exactly parallel to the tangent. I'm generating vectors that are actually tangent to the circle. So in reality, these vectors are pointing in the same direction. But if you can imagine this, a different field where the force maybe wasn't exactly tangent, I might get a picture like this. And so there would normally be an angle between those two. And what we're trying to measure is how much of this force is pushing in the same direction as t, right? Because remember, you can break down a force into part of it's moving in the same direction, part of it is moving perpendicular to that direction. In this case, it's entirely moving in that direction. But if it wasn't, how do you capture how much of one vector is in the same direction as another vector? If you recall from 21C, that's given by the dot product. And so our formula for circulation is we're going to dot those two. It's F dotted with T times a little unit of arc length. That's what ds means. There's sort of two formulas. This is more of the theoretical formula, and then sort of the more user-friendly. Traveling a little distance along the tangent vector along the arc of the circle is equivalent to dotting this with just, if r of t is the equation of the circle, taking the derivative of it produces that tangent line. So you'll see these formulas. This is more the theoretical formula. And this is the more one, the one that we use, user friendly. So it's just a dot product. That's what a dot product does, is it measures how much of this field is acting in the direction of our curve that our particle is moving along. Now, there is another version of this formula that our book talks about, which is kind of handy because we're always going to use this if we're going to calculate circulation or flow. If my field F is denoted as capital M, capital N, and my position curve is just, this is going to track the X value, this is going to track the Y value. Doesn't necessarily have to be XY, but if that's measuring X, that's measuring Y, we're going to dot it with dr, which would be dx dt, dy dt. So then my circulation, if I dot F with dr, remember the dot product just multiplied the X components and add the product of the Y components. So it would be M times dx dt, this times this, plus N times dy dt, which shorthand notation for that, we could just write this as the line integral around the curve. Sometimes some books use, we talked about this in a previous video, some books use that for a line integral, or you can just put an integral with a curve there. You can put them both if you want to really emphasize it. Shorthand notation, it would just be m dx plus n dy. So for our particular example, we do need to get a parameterized curve for our unit circle. And so this goes back earlier videos. To parameterize a circle, the simplest way to do it is to let X be either sine or cosine and Y be the other one. If I wanted to start at 1, 0, just like the unit circle in trig, then I'm going to let X be cosine t, Y be sine t. And that would be true for t between 0 and 2 pi if I wanted to measure one leap around the circle. Now I'm going to do this for this original field here. The field was negative yx. So on this curve, if f is negative y comma x, then that means f is really negative sine of t. This is x, this is y. And then cosine of t. So my formula for circulation has me dotting f with dr. And I'm going to do this, it's all going to be in terms of t. So I'm going to do it one time around the circle. So that's going to be the integral from 0 to 2 pi of my f, negative sine t, cosine t, dotted with dr. I haven't done that yet. So dr would be the derivative of each of those. That's going to be negative sine t for cosine, cosine t, dt. If I do the dot product, I get negative sine times negative sine is sine squared plus cosine squared, which happens to be 1. Antiderivative of that is just t from 2 pi to 0, gives me an answer of 2 pi. So that would be a quantitative measure of the flow or the circulation around the circle with that field. And we do denote with circulation, the fact that it's positive means we'll call that positive is a counterclockwise. Counterclockwise, sometimes denoted CCW. If it was negative, then we would interpret that to be counterclockwise, clockwise flow or circulation. Now let's contrast that. I want you to see the difference. How much circulation you get really depends on, well, the graph, the curve, but also on the field. that we're using. So now let's find the circulation on the same unit circle, cosine of t sine t, but this time for the field xy. That was a field we discussed on the previous video talking about vector fields. If you pick points around the circle, the unit circle, like 1, 0, you're going to get the vector 1, 0, and that's a vector that points directly away. If you pick a point here, you're going to get the same x and y value. You're going to get a vector that's essentially pointing in the direction of 1, 1. This is our radial field. It's pointing directly away from the origin. And, you know, again, it's not just on the outside, right? There's shorter vectors on the inside because your x and y are not as big. And they get longer as you move away. But just from an intuitive standpoint, if we think of circulation as flow, is how much does this force cause this particle to move around the circle? If I put a particle there and it's getting subjected to a force, you know, if I put a little vector there, it looks like the vector is just basically pushing it directly away. It's not pushing it counterclockwise or clockwise. So from an intuitive perspective, you might already figure out what the answer should be, in that if there's nothing pushing it around the circle, no matter where this particle is, right? When the particle's here, it's getting pushed directly outward. When it's here, it's getting pushed outward. It's not getting pushed left or right. You might intuitively suspect that the circulation around this circle is 0, and you would be correct. So let's confirm that. So on R of t, my field would be, it's xy, so it's just going to be cosine t sine t. And my circulation is the line integral around my curve of f dotted with dr. So we'd once again go from 0 to 2 pi. And I would dot cosine t sine t, that's my f, with dr, which is negative sine t, positive cosine t. If I do that, I end up with cosine t times negative sine t, so negative cosine t sine t, plus sine t times cosine t. These are just negative and opposite, so this just gives me the integral of 0, and the integral of 0 is dt is going to be 0. So as we suspected, that is the circulation. And again, how would we have suspected that? I'll try to put that in words again, is that, but note, the vectors are pushing the particle away from the circle, not around the circle. That's how we can interpret why that answer was 0. Whereas if you looked at the other one, I mean, the other one was probably the most pure form, probably the biggest circulation you can get, because my vectors on the other one were pushing it tangent to the circle. That's about as good as you can do. I always think about if you're pushing a kid on a merry-go-round or something, right? What you want to do, if you want to get them to go as fast as possible, is you should apply your force directly tangent to the circle, and that's going to spin the circle as fast as possible. But you would not want to pull on the merry-go-round. That's not going to make it twist at all, right? So there is some intuitiveness to these if you want to think about it that way. Not always, depending on the type of problem, can you visualize things like this so easily. Let's take that same radial field that we just talked about, and let's calculate the circulation for a different curve. We're going to use the parabola y equals x squared from 0, 0 to the 0.39. So this is the same radial field that we used on the previous one. So I'm just going to imagine some vectors here. Remember, they're going away from the origin. They're getting bigger as you move away. So, if I was at an angle here, it'd be this getting bigger. And you can kind of imagine if there was a particle somewhere on this parabola, that there is one of those vectors is going to hit it and it's going to push it, right? Not always in the perfect direction to get it to move the fastest, but there's some movement that's going to be pushing it along this curve. So I do expect some kind of a circulation here. In order to calculate that, I do need to parameterize this parabola. I should do that, parameterize. So this goes back to earlier stuff. Remember, for something like y equals x squared, the parameterization is really easy. If we just let x be t, then y is just going to be t squared because y is x squared. And since x is t, I would want and x goes from 0 to 3, I would want my bounds for t to go from 0 to 3 as well. So this could become my r of t. Is just t squared with those bounds for t. We might as well do dr since that's going to be in the formula. That's going to be the vector 1, 2t. And then also remember that on my curve, on r of t, my field will be a function of t as well. And this is x, this is y. So if my field is xy, it's just going to be the field t squared. So my circulation is the line integral of f of t squared dotted with dr 1, 2t, and that's going to go from, I'll put limits on this, from t equals 0 to 3 because that's how we parameterized our parabola. Doing the dot product, looks like I get t plus 2t cubed, which is t squared over 2. That's going to be 2t to the 4th over 4. So that's basically t to the 4th over 2 if I simplify it. From 3 to 0 gives me, let's see, 9 halves plus 81 halves minus, if I plug in 0, nothing. So that's 90 halves. So I get a circulation of 45. It's tough to, what does that compare? I don't have anything really to compare that to, but it's a value. And it is positive. It's kind of pushing it sort of counterclockwise around this thing. The negative answer could interpret as maybe pushing it the other way along that curve. Hey, a note from 21C, possibly 21B. In 21C, though, they use as one of their examples for the dot product that a physics concept called work. How much work you do when you move an object is basically the force dotted with the distance. Now, if I was moving, what we've been talking about is a force moving a particle along a curve, right? Some fields. And so I'm moving at little tiny distances, right? I break it up into little tiny distances as this field moves this particle. And so to get the total work, I can integrate over the line integral, and it's the force dotted with the distance is dr, which means that's the same formula we use for circulation. So I just wanted to make a note here because they could ask you to calculate the work done with a certain field in moving a particle a certain distance, but it's the same formula as circulation. Work, same formula as circulation. So we'll do one final example with work. This one's a 3D example. Can't really sketch out anything here that's gonna. That field is much more complicated in 3D. I don't have no idea what it looks like. But that's a force that's acting on, let's assume, a particle. And we're trying to calculate how much work is done in moving this particle from the point 123 to the point 503 on a straight line path. Recall another common parameterization, something you'd be expected to do on your own, is to parameterize a line segment. So to review that, let's pretend our particle is right here when t is equal to 0, and it's moving at a constant speed, and by the time it gets to here, this is 1 unit of time later. So that if I keep track of x, it started at 1, and every unit of time, it's going to gain 4. So that would be 4t. So in other words, if I went another second of time, unit of time, I could expect my x-coordinate to be 9, because it went from 1 to 5, gained 4, and the next unit of time, it should gain another 4. For y, it's starting at 2. It lost 2 units in that 1 unit of time, so it would lose 2 units in every unit of time. And my z value, it looks like it's always 3. It doesn't matter on time. And this would be true from 0 to 1. That's the easiest way to parameterize this. So then I can just turn this into a vector valued function for position 1 plus 4t, 2 minus 2t, 3. I have to evaluate on my straight line path. My function is x, y, y, negative xz. This is keeping track of the x coordinate, y coordinate, z coordinate. So this is x, right? This is y. This is z. So on R of t, f is going to equal x times y, 1 plus 4t times 2 minus 2t, just y, 2 minus 2t, and negative yz, so negative 2 minus 2t times 3. We might want to simplify this because we're going to have to do the dot product. So if I FOIL this out, I know you can multiply things out. I think I'm going to get negative 8t squared minus 2t plus 8t. So that's plus 6t and then plus 2. This is negative 3. Basically, I'll just distribute that. So that's negative 6 plus 6t. And then finally, I do need dr dt because I'm going to dot it with that. So dr dt, back to this, just taking the derivative of x, y, and z, I'm going to get 4, negative 2, 3. So work is the line integral of f dotted with dr. Our parameterization is going from 0 to 1, so I need to dot negative 8t squared plus 6t plus 2, 2 minus 2t, negative 6 plus 6t, dotted with 4, negative 2, 3. Oh, wait, whoa. Almost made a big mistake. What is the derivative of 3? That's actually 0, isn't it? So this should be a 0 here. That's actually going to make life a little bit easier. But when I do this dot product, it's just going to be this times 4. So 4 times negative 8t squared plus 6t plus 2. Then this times negative 2, so minus 2 times 2 minus 2t. But then I get this times 0 plus 0. So I don't have to worry about that. Okay, I know you can integrate. Work this out. I got a final answer if I'm correct of 22/3. Please let me know in the comments if you get something different. I go back and check it. Okay, next up, we'll start to talk about another big topic, which is flux.